quite substantially reduced. And can we use all that to go through? The second part is to use the gamma value of 30 to go through and try and solve this equation and work out what the velocity is that the person's travelling at. So a little bit of substitution, a little bit of rearranging and a bit of magic, and we come out there that the value here is the final velocity in terms of speed of light. So to get to that extent where you've got a gamma value of 30, you actually have to be travelling at 3 9s and 2 4s the percentage of light as value. So extremely high. So it's not going to happen. What did I look at yesterday? I think, trying to think that 50% of the speed of light is only a gamma value of about 0.15 or something. It's not that high. So we need to be cognizant of that as we go through. Any questions on that little bit? I mean, once again, that's just a matter of you starting to think about this example. It still is. Here we are on Earth. There's a meter. I'm now in space. You see the same meter. I'm now travelling at 0.95 the speed of light. This is going to go down by effectively 30 times in length. So it's only going to be 3 centimetres long, 3.3 centimetres long. Right? That takes a fair bit for you to grasp. We're going to come back to this and revisit when we do some energy later on. We have to talk about what the effect is on high and fast particles on the Earth. The next little example here is an example of something that actually does happen, and that is that there's a linear accelerator in the Stanford University that's 3 kilometres long. It turns out that when you get an electron travelling down there at the velocity that it travels at, the relativistic change in length goes from 3,000 metres down to 0.5 metres. So there's a fairly big gamma conversion between those two.